At the very beginning of our understanding of nature, humans noticed something strange long before atoms were known to exist. Amber rubbed with fur could attract small bits of straw. Lightning could tear the sky apart. Certain materials pushed or pulled without touching. These observations were the earliest hints of electric charge, a property so fundamental that it shapes the structure of the universe, yet so subtle that its true origin remained hidden for centuries. The question is not just how charge behaves, but why it exists at all, and why nature allows only two opposite types instead of many. Electric charge is not an object and not a substance. It is a way matter interacts with a specific force, the electromagnetic force. To understand why this force exists, physics takes us deeper than atoms, deeper than particles, into the idea that the universe is governed by symmetries. A symmetry in physics does not mean something looks pretty or balanced. It means that certain transformations do not change the underlying laws. One of the most powerful symmetries ever discovered is related to electromagnetism, and from this symmetry, electric charge emerges naturally, almost inevitably. In modern physics, empty space is not truly empty. It is filled with invisible fields that exist everywhere, even in total darkness. One of these is the electromagnetic field. Particles are not isolated dots moving through space. They are excitations of deeper quantum fields. The electron, for example, is an excitation of the electron field, and its charge comes from how this field couples to the electromagnetic field. This coupling is not optional. It is built into the mathematical structure of reality. The moment such a field exists, charge becomes unavoidable. The reason nature has only two types of electric charge lies in the way the electromagnetic field works. The field responds to a single kind of symmetry, and that symmetry allows only two directions of interaction. These directions manifest as positive and negative charge. They are not labels chosen by humans. They are opposite signs in an equation that describes how fields interact. One sign produces attraction toward the field in one direction. The opposite sign produces attraction in the reverse direction. There is no third option because the symmetry does not allow it. This is deeply connected to the idea of gauge invariance, one of the central principles of modern physics. Gauge invariance means that certain changes in the mathematical description of a field do not alter physical reality. To preserve this invariance, the universe must include a force carrying field and particles that interact with it in specific ways. Electric charge is the measure of how strongly and in which direction a particle interacts with the electromagnetic field. Positive and negative charges are not different substances. They are opposite ways of responding to the same underlying field. If electric charge were not quantized, meaning it did not come in fixed units, the universe would be chaotic. Atoms would not form stable structures, because electrons could orbit nuclei at unpredictable strengths. Chemistry would not exist as a reliable process. The fact that charge comes in discrete units is another clue that it is rooted in deep symmetry rather than accident. The electron carries the smallest unit of free negative charge, and all other charges are exact multiples of this value. This precision hints at a fundamental rule written into the fabric of reality. The existence of two opposite charges also explains why the universe is stable rather than tearing itself apart. Like charges repel, unlike charges attract. This simple rule allows matter to form complex structures. Electrons bind to protons, creating atoms. Atoms bind together, forming molecules. Molecules form cells, and cells form living organisms. If all charges were the same, or if there were many incompatible types, this elegant hierarchy would collapse. The universe would be either a featureless cloud or a violent storm of forces with no stable patterns. From a deeper perspective, electric charge exists because the universe demands consistency. Conservation of charge is not just an observed rule, it is a consequence of symmetry over time. Because the laws of physics do not change from one moment to the next, charge must be conserved. This means the total charge of the universe remains constant. Particles can be created or destroyed only in ways that preserve this balance. This is why electrons and positively charged particles are often created in pairs. Nature keeps perfect accounts. The idea that charge is fundamental does not mean it is unexplained. It means it is explained at the deepest level currently known. Asking why charge exists is like asking why space has dimensions or why time flows forward. At some point, explanations reach a bedrock of principles that simply are. However, modern physics shows that charge is not arbitrary even at this level. It arises naturally once certain symmetries are assumed. In that sense, charge is less a mystery and more a logical necessity. What makes this even more profound is that electromagnetism is just one of several fundamental forces, yet it is the only one that produces long-range effects at everyday scales. Gravity is weak, the nuclear forces are confined to tiny distances, but electromagnetism reaches across space. This dominance is directly linked to charge. Because electric charge comes in two opposite types, large-scale neutrality emerges. Objects contain roughly equal amounts of positive and negative charge, allowing electromagnetic forces to cancel out over long distances, leaving gravity to shape galaxies. Without this balance, the universe would look completely different. The origin of electric charge also ties into the early universe. In the first moments after the Big Bang, energy condensed into particles and fields. The symmetries of nature were already present, dictating what kinds of particles could exist and how they could interact. Charge was not added later, it was part of the initial conditions. As particles formed, their charges were fixed by the fields they belonged to. This means the structure of matter today reflects decisions made by the universe at its birth. Perhaps the most striking aspect of electric charge is how deeply it connects mathematics and reality. The equations that describe electromagnetism are elegant, simple, and astonishingly accurate. They predict waves that travel at the speed of light, unify electricity and magnetism, and explain everything from radio signals to atomic bonds. Charge appears in these equations not as an afterthought, but as a central character. Remove it, and the equations lose meaning. Change its nature, and the universe becomes unrecognizable. When we say electrons are negative and protons are positive, we are summarizing a vast chain of logic that stretches from quantum fields to cosmic structure. These signs are not preferences. They are reflections of how the universe is wired. The existence of two opposite charges is the simplest solution to the requirement of interaction without instability. Nature tends to favor simplicity when it leads to consistency, and electric charge is a perfect example of this principle. Even today, physicists continue to explore whether electric charge is truly fundamental or whether it emerges from something even deeper. Some theories suggest that charge might arise from higher dimensional geometry or from more abstract symmetries beyond current understanding. Yet every experiment so far confirms the same pattern. Charge is conserved, quantized, and always comes in two opposite forms. The universe seems remarkably confident in this choice. In the end, the origin of electric charge is not just a story about particles. It is a story about why the universe holds together instead of dissolving into chaos. It explains why matter can exist, why light can travel, and why information can be transmitted across space. Charge is the invisible rule that allows complexity to arise from simplicity. Without it, there would be no atoms, no chemistry, no stars, and no observers to ask these questions. This is only the first layer of the mystery. Beneath it lies an even deeper connection between charge, mass, and the forces that shape reality. But even at this level, one truth becomes clear. Electric charge exists because the universe could not function without it, and it exists in two opposite forms because that is the only way balance, structure, and stability can emerge. Long before electrons and protons were imagined as tiny balls with plus or minus signs attached to them, physics underwent a quiet revolution that completely changed how matter is understood. The modern picture does not begin with particles at all. It begins with fields. According to quantum field theory, the most successful framework ever created to describe nature, the universe is not made of particles moving through empty space. Instead, space itself is filled with continuous fields, and what we call particles are small, localized excitations of those fields. This shift in perspective is the key to understanding why electrons are negative and protons are positive, not as an arbitrary choice, but as a necessary outcome of how these fields interact. Every fundamental particle corresponds to its own quantum field that exists everywhere in the universe. Even in the deepest vacuum, far from stars and atoms, these fields are still present. An electron is not a tiny object floating in space. It is a vibration of the electron field. A proton, more complex in structure, arises from interacting quark fields bound together by another field known as the strong force. The charge of these particles is not painted onto them afterward. It is encoded directly in how their fields are allowed to interact with the electromagnetic field. The electromagnetic field is special because it is tied to a deep symmetry of nature. This symmetry is so fundamental that once it exists, it forces certain rules on everything else. Fields that obey this symmetry must interact with the electromagnetic field in a precise way, and that interaction defines electric charge. In this sense, charge is not a substance carried by particles. It is a relationship between fields. To grasp this, imagine a universe with an electron field but no electromagnetic field. In such a universe, electrons could still exist as excitations of their field, but they would not have charge. They would not attract or repel anything electrically. The moment the electromagnetic field is introduced, however, the electron field must either interact with it or remain completely invisible to it. If it interacts, the strength and direction of that interaction becomes the electron's charge. The mathematics of the theory allows only specific types of interaction, and those interactions come with a sign. That sign is what we call negative or positive charge. The electron field couples to the electromagnetic field with a specific sign that we label as negative. This sign determines how electrons respond to electric and magnetic forces. Flip the sign, and you get a particle that behaves like a positron, the electron's antimatter counterpart. The positron is not a different kind of field. It is a different excitation of the same underlying structure, responding to the electromagnetic field in the opposite way. This reveals something profound. Positive and negative charge are not separate categories of matter. They are opposite orientations within the same mathematical framework. Protons, at first glance, seem to be a different story. Unlike electrons, protons are not elementary particles. They are made of quarks, bound together by the strong force. Yet their positive charge is just as precise and just as fundamental in its effects. The explanation again lies in quantum fields. Each type of quark corresponds to its own field, and each quark field carries a specific electric charge. Some quarks have positive fractional charge, others negative fractional charge. When quarks combine to form a proton, the sum of their charges results in exactly one positive unit of charge. This is not a coincidence or a numerical accident. The allowed charges of quarks are dictated by the same underlying symmetry that governs electrons. The electromagnetic field does not care whether it is interacting with an electron field or a quark field. It only cares about how that field transforms under its symmetry. Once that transformation rule is fixed, the charge is fixed. The proton ends up positive because the quark fields that form it are required to have those specific charges for the theory to remain mathematically consistent. One of the most astonishing aspects of this framework is that the total charge of the electron and the proton match in magnitude exactly. This equality has been tested to extraordinary precision, far beyond what everyday experience could ever suggest. The reason for this equality is not experimental coincidence, but theoretical necessity. If the magnitudes differed even slightly, the equations describing the electromagnetic field would break down. Atoms would not be stable. The universe would not be internally consistent. Quantum field theory does not merely allow equal charges, it demands them. The idea that fields decide charge might sound poetic, but it is literally true in the mathematical sense. The equations that describe these fields include terms that specify how strongly and in which direction they interact with the electromagnetic field. These terms cannot be chosen freely. If chosen incorrectly, the theory becomes inconsistent, producing infinities that cannot be removed or predictions that contradict observation. Only certain charge values produce a stable, predictive theory. Nature appears to have chosen one of the simplest possibilities. Another layer of this story involves the idea of renormalization. In quantum field theory, interactions between fields occur at all energy scales, from the very small to the very large. When physicists calculate the effects of these interactions, they often encounter infinities. Renormalization is the process by which these infinities are absorbed into redefinitions of physical quantities like mass and charge. Remarkably, this process works only because charge behaves in a very specific way. The fact that electric charge can be consistently renormalized is another indication that it is deeply rooted in the structure of quantum fields rather than being an arbitrary parameter. From this viewpoint, asking why electrons are negative and protons positive is similar to asking why a wave has a crest and a trough. The sign of the charge indicates the phase of the field's interaction with the electromagnetic field. Positive and negative charges are like opposite phases of the same underlying phenomenon. They are defined relative to each other, not in isolation. This is why the choice of which sign we call positive is a convention, but the existence of two opposite signs is not. The neutrality of the neutron further reinforces this field-based picture. A neutron is composed of quark fields just like the proton, but arranged differently. The charges of its constituent quarks cancel out exactly. From the perspective of the electromagnetic field, the neutron's combined interaction sums to zero. Yet inside the neutron, charged fields are constantly interacting. This shows that charge is not about what particles are made of in a material sense, but about how their fields collectively respond to the electromagnetic field. One of the most powerful ideas connecting quantum fields and charge is symmetry conservation. The symmetry associated with the electromagnetic field leads directly to the conservation of electric charge. This means that no matter how fields interact, split, or combine, the total charge remains constant. In particle reactions, this rule is never violated. Electrons can annihilate with positrons, converting their energy into light, but the charges always cancel perfectly. New charged particles can be created, but only in combinations that preserve the total charge. This conservation law is not imposed from outside. It emerges automatically from the symmetry of the fields. In the early universe, when temperatures were unimaginably high, quantum fields behaved differently than they do today. Symmetries that are hidden at low energies were fully exposed. As the universe cooled, some symmetries broke, giving rise to the distinct forces and particles we observe now. However, the symmetry underlying electromagnetism survived this transition. As a result, electric charge remained a defining feature of matter from the earliest moments of cosmic history. The charges of electrons and protons were fixed long before atoms existed. This field-based understanding also explains why charge is so stable. An electron cannot gradually lose its negative charge, and a proton cannot slowly drift toward neutrality. Their charges are tied to the identity of their fields. To change the charge would require changing the field itself, effectively turning the particle into a different kind of excitation. This is why charge is one of the most conserved and reliable quantities in all of physics. At a deeper philosophical level, quantum fields blur the distinction between what is fundamental and what is emergent. The electron feels fundamental because it is elementary, but its charge feels equally fundamental even though it arises from interaction. In this sense, charge is both basic and relational. It is basic because it cannot be reduced to anything simpler within the theory, and relational because it only has meaning in the context of a field interacting with another field. When we say that quantum fields decide the charge of electrons and protons, we are really saying that the universe enforces a strict internal logic. Once certain symmetries are in place, everything else follows. Electrons must be negative, protons must be positive, and their charges must match in magnitude. These facts are not added by hand. They emerge from the demand that the equations describing reality make sense and remain consistent at all scales. This realization transforms a familiar classroom fact into something profound. The plus and minus signs attached to particles are not decorative symbols. They are visible traces of invisible fields filling all of space, obeying symmetries that were set at the birth of the universe. Every spark, every chemical bond, every nerve signal in the human body is a quiet confirmation that those symmetries still hold. This is only half of the story. Beneath these interactions lies an even deeper connection between charge, force carriers, and the geometry of spacetime itself. But even at this level, one truth stands out clearly. The charge of electrons and protons is not chosen by chance. It is dictated by the quantum fields that define what matter is and how it can exist at all. At first glance, the neutron appears to be the simplest resident of the atomic nucleus. It carries no electric charge, does not attract or repel electrons, and often feels like a passive bystander compared to the active push and pull of protons and electrons. Yet this apparent simplicity hides one of the most subtle and fascinating stories in modern physics. The neutron is not neutral because it lacks charge internally. It is neutral because of a perfect and deeply constrained balance of charged components working together in a way that preserves the laws of the universe. To understand this, we must abandon the idea that particles are indivisible points. Protons and neutrons are not fundamental in the same way electrons are. They are composite objects, built from smaller entities called quarks. These quarks are not abstract mathematical tricks. They are real physical components with measurable properties, including electric charge. What makes the neutron remarkable is not the absence of charge, but the way charge cancels itself so precisely that, from the outside, nothing remains. A neutron is made of 3 quarks, just like a proton. The difference lies in which quarks are present and how they are arranged. Quarks come in different types, each with a specific electric charge. Some carry positive fractional charge, others carry negative fractional charge. In the neutron, the combination of quarks includes both positive and negative charges that add up to exactly 0. This is not an approximation. It is an exact cancellation enforced by the same rules that govern all particle interactions. This exactness matters. If the neutron's internal charges failed to cancel even slightly, atoms would behave very differently. Neutral atoms would not be neutral. Matter would slowly drift under electromagnetic forces. Chemistry would be distorted. The fact that none of this happens tells us that the neutron's neutrality is not accidental. It is the result of strict conservation laws and deep symmetries that leave no room for error. Inside the neutron, the charged quarks are not sitting still. They are in constant motion, bound together by the strong nuclear force, one of the most powerful forces in nature. This force is mediated by particles called gluons, which themselves carry energy and momentum. The interior of a neutron is a seething, dynamic system, more like a storm than a solid object. Despite this chaos, the overall electric charge remains exactly 0 at all times. The electromagnetic field sees only the total, and the total is perfectly balanced. This leads to an important realization. Electric neutrality does not mean electrical emptiness. The neutron interacts with electric fields in subtle ways. It can be polarized, meaning its internal charges can shift slightly in response to external fields. This behavior has been measured experimentally and confirms that the neutron contains charged components. Yet, because these shifts always preserve the total charge, the neutron never behaves like a charged particle. It remains neutral in its net interaction with the electromagnetic field. The reason this balance is so stable lies in the structure of the underlying quantum fields. Quarks are excitations of quark fields, and these fields carry fixed charges dictated by the symmetry of the electromagnetic interaction. A quark cannot change its charge without becoming a different kind of quark altogether. This rigidity ensures that when quarks combine, their charges add in predictable ways. The neutron exists as a stable configuration because its quark content satisfies all required conservation laws simultaneously. One might wonder why nature allows such a configuration to exist at all. Why not make everything either positive or negative? The answer lies in the role neutrons play in stabilizing matter. Protons repel each other electrically because they carry the same positive charge. If atomic nuclei were made only of protons, they would fly apart. Neutrons provide a solution. They contribute to the strong nuclear force, which binds nuclei together without adding additional electric repulsion. This delicate balance allows heavy elements to exist and makes the rich diversity of matter possible. The neutrality of the neutron is therefore not just a curiosity, it is a necessity. Without neutral particles capable of participating in the strong force, atomic nuclei would be extremely limited in size. Elements beyond hydrogen would struggle to exist in stable forms. Stars would burn differently, and the chemical complexity required for life would never emerge. The neutron's lack of net charge is one of the quiet conditions that make the universe habitable. At a deeper level, the neutron's neutrality reflects a broader principle in physics. Observable properties depend on how systems interact with fields, not on their internal composition alone. From the perspective of the electromagnetic field, only total charge matters. The field does not respond to internal details unless they affect the overall interaction. This is why a neutron behaves as neutral even though its interior is electrically active. The electromagnetic field averages over the complexity and responds only to the net result. This principle shows up repeatedly in physics. Composite systems often exhibit properties that are not obvious from their parts. Temperature emerges from molecular motion, pressure emerges from countless collisions, and neutrality emerges from internal charge balance. The neutron is a textbook example of emergence at the subatomic level, where complex internal dynamics give rise to a simple external property. There is also a deep connection between neutron neutrality and charge conservation. In all known interactions, electric charge is conserved exactly. When particles transform or decay, the total charge before and after remains the same. The neutron itself can undergo decay under certain conditions, transforming into other particles. Even then, the total charge is preserved perfectly. This unwavering consistency reinforces the idea that neutrality is not a fragile state, but a protected one. The existence of neutral composite particles also highlights the difference between fundamental and effective properties. The neutron's neutrality is an effective property, meaning it describes how the neutron behaves in interactions, not what it is made of at the deepest level. This distinction is crucial in modern physics, where many observable features emerge from deeper layers of structure. Understanding this helps avoid the misconception that neutrality implies simplicity. In experimental physics, the neutron's neutrality has been both a challenge and an opportunity. Because neutrons do not respond strongly to electric fields, they can penetrate matter deeply, making them powerful probes of atomic and nuclear structure. Neutron scattering experiments have revealed details of materials, magnetic ordering, and nuclear forces that would be inaccessible using charged particles. This practical usefulness stems directly from the neutron's balanced internal charge. From a cosmic perspective, neutrons played a critical role in the early universe. Shortly after the Big Bang, protons and neutrons formed in nearly equal numbers. As the universe cooled, some neutrons decayed, but many were captured into atomic nuclei during the formation of the first elements. Their neutrality allowed them to combine freely with protons, shaping the initial chemical makeup of the cosmos. Without neutral neutrons, the elemental abundance of the universe would look entirely different. The neutron also teaches an important lesson about how nature hides complexity behind simplicity. A neutral particle might seem boring compared to a charged one, but its neutrality is the result of finely tuned internal relationships. It is a reminder that what we observe on the surface is often a summary of deeper processes, not a full description. In this sense, the neutron is one of the most elegant examples of balance in the universe. Even today, physicists continue to study the neutron in search of tiny deviations from perfect neutrality. Any such deviation would signal new physics beyond current theories. So far, every measurement confirms the same result. The neutron's net charge is zero to an astonishing degree of precision. This consistency strengthens confidence in the underlying framework of quantum field theory and the symmetries that govern charge. Ultimately, the neutron's neutrality is not a passive absence, but an active balance. It exists because charged components are arranged in exactly the right way, under exactly the right rules, enforced by the deepest laws we know. This balance allows neutrons to stabilize matter, shape nuclei, and influence the evolution of the universe without dominating it electrically. In understanding why the neutron is neutral despite being made of charged particles, we uncover a broader truth about reality. Nature often achieves stability not by eliminating opposing elements, but by arranging them in perfect harmony. The neutron stands as a quiet proof of this principle, a particle whose silence in the electromagnetic world speaks volumes about the order hidden within the universe. From the smallest scales of subatomic particles to the vast structure of the cosmos, one rule operates with unwavering consistency. Electric charge is never lost, never created from nothing, and never altered without balance. This rule, known as charge conservation, is so deeply embedded in the laws of nature that no confirmed experiment has ever observed a violation. It is not merely a habit of particles. It is a reflection of a profound symmetry that governs how the universe is allowed to behave. To understand why charge conservation exists, we must look beyond particles and forces and examine time itself. In physics, symmetries are not aesthetic features. They are constraints that dictate what is possible. One of the most important insights in modern science is that whenever a system behaves the same way over time, certain quantities must be conserved. Because the laws of electromagnetism do not change from one moment to the next, electric charge cannot change either. Conservation is not enforced by particles. It emerges from the unchanging nature of physical law. This connection between symmetry and conservation is one of the deepest discoveries in physics. It reveals that charge is not protected by a rule added from outside, but by the structure of reality itself. As long as the electromagnetic laws remain the same today as they were yesterday, charge must be conserved. If charge were to vanish or appear spontaneously, it would signal a breakdown of the universe's consistency. Time would no longer be uniform, and physics would lose its predictive power. At the level of everyday experience, charge conservation appears simple. When an object becomes charged, it has not created charge from nothing. It has transferred charge from somewhere else. Rubbing a balloon on fabric moves electrons, leaving one surface negatively charged and the other positively charged. The total charge before and after remains the same. What seems like creation is merely rearrangement. At the subatomic level, the same principle holds with absolute precision. When particles interact, collide, or decay, charge accounting is perfect. In high-energy experiments, particles can transform into entirely different particles, yet the total charge always balances. When matter meets antimatter, particles annihilate into energy, but even then, charge disappears only because equal and opposite charges cancel each other out. The universe never allows an imbalance to survive. This exactness points to something deeper than mechanical bookkeeping. In quantum field theory, charge conservation arises from the symmetry of the electromagnetic field under certain transformations. These transformations do not change observable physics, yet they require that charge remain constant. The mathematics leaves no room for exceptions. Any violation would make the theory inconsistent, producing contradictions and infinities that cannot be resolved. One of the most remarkable consequences of charge conservation is the stability of matter. Electrons do not suddenly detach from atoms because their charge cannot simply disappear. Protons remain protons because their positive charge is an essential part of their identity. If charge conservation were only approximate, atoms would gradually decay into chaos. The fact that matter remains stable over billions of years is a direct result of this unbreakable rule. Charge conservation also explains why particles are often created in pairs. In energetic environments, such as the early universe or particle accelerators, energy can convert into matter. When this happens, particles with opposite charges appear together. An electron does not appear alone. It is accompanied by a positively charged partner. This pairing is not a preference but a necessity. The universe allows creation only if balance is preserved. The symmetry underlying charge conservation is subtle but universal. It applies everywhere and at all times. Whether in the core of a star, inside a human cell, or in the emptiness between galaxies, the same rule applies. This universality gives charge a special status among physical quantities. It is not dependent on environment, scale, or history. It is a global constraint written into the fabric of existence. The reliability of charge conservation has allowed scientists to build extraordinarily precise technologies. Electrical circuits, communication systems, medical imaging, and computing all depend on predictable charge behavior. Every calculation assumes that charge will behave tomorrow exactly as it does today. The success of these technologies is indirect evidence of the deep symmetry protecting charge. At the cosmic scale, charge conservation shapes the structure of the universe. Despite the presence of countless charged particles, the universe appears electrically neutral on large scales. This neutrality is not accidental. Any large imbalance would produce enormous electric forces, dramatically altering cosmic evolution. Charge conservation, combined with the tendency of opposite charges to attract, leads naturally to large-scale neutrality, allowing gravity to dominate the architecture of galaxies and clusters. There is also a philosophical dimension to charge conservation. It suggests that nature values balance over convenience. The universe permits dramatic transformations, violent collisions, and radical changes in form, but it never compromises certain fundamental constraints. Charge conservation is one of these constraints, standing alongside the conservation of energy and momentum as pillars of physical law. In extreme conditions, such as near black holes or in the earliest moments of the universe, physicists test whether these conservation laws still hold. So far, every observation supports the same conclusion. Even under the most extreme circumstances, charge conservation remains intact. This resilience hints that the symmetry protecting charge is among the most fundamental features of reality. Charge conservation also connects directly to the identity of particles. A particle's charge is not an accessory that can be removed. It defines how that particle interacts with the electromagnetic field. To change a particle's charge would require changing the underlying field it belongs to. This is why particles with different charges are considered different species. Conservation ensures that these identities remain consistent through interactions. The idea that a simple symmetry can enforce such a powerful rule is one of the triumphs of modern physics. It shows that complexity does not require complexity at the foundation. A single, elegant symmetry can shape the behavior of the entire universe. Charge conservation is not a fragile rule that could have been otherwise. It is a natural consequence of a universe that behaves consistently over time. As our understanding deepens, physicists continue to explore whether charge conservation is absolutely exact or part of an even larger framework. Some speculative theories suggest scenarios where familiar symmetries might be embedded in higher structures. Yet any such theory must reproduce the extraordinary precision of charge conservation observed today. The burden of proof is immense because the existing evidence is overwhelming. In the end, charge conservation is not just a technical detail of electromagnetism. It is a statement about order in the universe. It tells us that beneath the apparent chaos of particles and forces lies a deep and unwavering consistency. Every spark of electricity, every chemical reaction, and every signal in the nervous system is a small expression of this cosmic rule. Understanding this keynote reveals why the universe is reliable enough to be studied at all. Without charge conservation, prediction would be impossible, and science itself would collapse. The fact that we can uncover laws, test them, and trust them across time and space is, in part, because electric charge obeys a symmetry that never breaks. When we look at electric charge only at the level of particles, it feels like a small technical detail. Electrons are negative, protons are positive, neutrons are neutral. But when this idea is followed to its deepest consequences, electric charge turns out to be a kind of fingerprint left by the universe on everything that exists. It quietly reveals the hidden structure of reality, showing how matter, forces, and even the existence of complexity are tied together by rules far deeper than atoms themselves. The presence of charge tells us that matter is not passive. Charged particles respond to fields, and fields respond back. This mutual interaction is the reason forces exist at all. Electromagnetism is not simply a force layered on top of matter. It is a relationship between charged fields that defines how matter can move, bind, and communicate. Every time two atoms form a molecule, every time light interacts with matter, electric charge is acting as the intermediary between structure and motion. One of the most striking revelations from studying atomic charge is how it exposes the layered nature of reality. Atoms appear solid and indivisible at human scales, but charge interactions reveal that atoms are mostly empty space held together by invisible forces. Electrons do not orbit nuclei like planets. They exist as probability clouds shaped entirely by electromagnetic interaction. The shapes of these clouds, and therefore the shapes of molecules, are determined by charge and nothing else. In this sense, the diversity of chemistry is a direct expression of electric charge arranging space itself. Charge also reveals that the universe prefers balance over uniformity. Positive and negative charges exist in equal measure, allowing matter to assemble into neutral structures. This balance is not imposed from outside. It emerges naturally from the way charges interact and conserve themselves. On cosmic scales, this leads to an electrically neutral universe, where electromagnetic forces cancel out and gravity becomes the dominant architect. Without this balancing act, stars, galaxies, and large-scale structure would be impossible. At the quantum level, charge exposes the limits of classical intuition. Particles with charge do not follow precise paths. They obey probability rules. Their interactions are mediated by the exchange of force carriers, quanta of the electromagnetic field. These exchanges are not optional or occasional. They are constant, happening even in the vacuum. This means that what we perceive as empty space is actually alive with charged activity, fluctuations, and interactions that shape reality behind the scenes. The existence of charge also hints at deeper unification. Electromagnetism was once thought to be separate from other forces, but it was later unified with the weak nuclear force in a single framework. In this unified picture, charge becomes part of a larger family of quantum numbers that describe how particles interact. This suggests that electric charge may be one aspect of a more general structure, a visible shadow of something even more fundamental. Charge further reveals that reality is governed by mathematical consistency rather than arbitrary choice. The values of charge are not free parameters that could be changed without consequence. They are tightly constrained by the requirement that the universe remains stable and predictable. Alter the charge of the electron even slightly, and atoms would either collapse or fail to bind. Change the charge balance between protons and electrons, and chemistry would vanish. The precise values we observe are not random, they are conditions for existence. The role of charge in information transfer is another profound clue. Every electronic signal, every nerve impulse, every photon interacting with matter relies on charge. Information in the physical world is carried by the movement and interaction of charged particles. This means that charge is not just about structure, it is about communication. The universe uses charge as a language, allowing systems to influence one another across space and time. Even life itself is inseparable from charge. Biological processes are driven by electric potentials, ion gradients, and molecular interactions governed by electromagnetic forces. The difference between living and non-living matter is not the presence of exotic particles, but the organization of charged interactions into self-sustaining patterns. In this way, electric charge forms a bridge between fundamental physics and biology, connecting the laws of the cosmos to the experience of consciousness. Charge also exposes the strange relationship between simplicity and complexity. The rules governing charge are astonishingly simple: two signs, strict conservation, precise quantization. Yet from these simple rules emerges the vast complexity of the material world. This is a recurring theme in physics, where a small set of principles generates endless variety. Charge is one of the clearest examples of how richness arises from restraint. On the frontier of modern research, physicists continue to ask whether electric charge is truly fundamental or an emergent feature of a deeper theory. Some approaches suggest that charge might arise from the geometry of extra dimensions or from topological features of space itself. Others explore whether charge is linked to deeper symmetries that also give rise to mass and space-time structure. While these ideas remain speculative, they all treat charge not as an isolated fact, but as a clue pointing beyond current understanding. The study of atomic charge also reshapes how we think about reality itself. It suggests that what we experience as solid objects are actually stable patterns of interaction, maintained by continuous exchanges of force. Matter is not static, it is dynamic equilibrium. Charge is the rule that keeps this equilibrium intact, preventing collapse while allowing interaction. When we follow the implications far enough, electric charge stops being just a property of particles and becomes a principle of organization. It determines what kinds of structures are possible, what kinds of processes can occur, and how complexity can persist over time. It is one of the quiet conditions that make a meaningful universe possible. This perspective changes how we interpret the simple facts taught in school. The statement that electrons are negative and protons are positive is not a trivial classification. It is a summary of deep truths about symmetry, interaction, and stability. It reflects a universe that is finely tuned not in the sense of fragility, but in the sense of coherence. In the end, atomic charge is a window rather than a wall. It does not close off inquiry, it invites it. Every time we probe charge more deeply, we uncover connections to other aspects of reality, from the early universe to the nature of life and information. It reminds us that the smallest features of nature often carry the biggest clues. By understanding atomic charge, we are not just learning why particles behave the way they do. We are learning how the universe organizes itself, how order emerges from simplicity, and why complexity is even possible at all. In that sense, electric charge is not merely a secret of atoms. It is one of the keys to understanding reality itself.